Hello students, imagine sipping a cup of tea that looks normal but has an unknown bitter taste. You'd immediately wonder what extra ingredients sneaked in. In the same way, organic compounds may carry hidden elements besides carbon and hydrogen, such as nitrogen, sulphur, halogens, or even phosphorus. To uncover these, chemists use qualitative analysis. The key is to convert these elements from their tightly held covalent forms into ionic forms, which are easier to detect with simple reagents. The most famous approach is Lassaigne's test, where we fuse the compound with sodium to unlock these hidden ions. By looking at color changes or precipitates, we confirm their presence. It's like turning invisible ink visible under a UV lamp. The element was always there. We just needed the right trick to reveal it. Let's begin with the most basic elements, carbon and hydrogen. To test them, we heat the organic compound strongly with copper to oxide. During this process, carbon is oxidized to carbon dioxide gas and hydrogen is oxidized to water vapor. The carbon dioxide gas, when passed through lime water, turns it milky because calcium carbonate precipitates. The water vapor, on the other hand, converts white anhydrous copper sulfate into bright blue hydrated copper sulfate. The balanced reactions are carbon plus to copper oxide gives to copper plus carbon dioxide and 2 hydrogen plus copper oxide gives copper plus water. These simple color changes in lime water and copper sulfate act as unmistakable signatures of carbon and hydrogen in organic compounds. Now, what about other elements like nitrogen, sulphur, and halogens? They do not reveal themselves so easily. That's where Lassaine's test comes in. The compound is fused with a small piece of sodium metal. The extreme reactivity of sodium breaks the covalent bonds holding these elements, converting them into ionic salts. Nitrogen forms sodium cyanide, sulphur forms sodium sulfide, and halogens form sodium halides. These salts dissolve in water to give the sodium fusion extract. This extract is like a treasure chest. Once opened, we can test each ion with suitable reagents. In essence, sodium acts as the liberator, pulling hidden atoms out of their covalent prison and turning them into testable forms. Let's put the sodium fusion extract to use, starting with nitrogen. If nitrogen is present, sodium cyanide forms during fusion. This cyanide ion reacts with ferrous sulfate to yield sodium ferrocyanide. On acidifying the mixture, ferric ions react with the ferrocyanide to produce a deep blue compound known as Prussian blue. The reactions are 6 cyanide ions plus ferrous ion give ferrocyanide ion, which then combines with ferric ions to produce ferric ferrocyanide, the Prussian blue precipitate. That striking blue color is a confirmatory test for nitrogen. But here's the catch: the acidification step is crucial. If you forget to add acid, the brilliant blue will never appear, and you may wrongly conclude that nitrogen is absent. Moving on to sulphur, the sodium sulfide in the extract can be detected in 2 ways. In the first method, when we add lead acetate solution, a black precipitate of lead sulfide forms, an unmistakable sign. In the second method, sodium nitroprusside solution reacts with sulfide ions to give a violet color. Now, here's a twist. If both nitrogen and sulfur are present in the same compound, the fusion produces sodium thiocyanate. This compound reacts with ferric ions to produce a blood red color. The key equations are sulfide ion plus lead to ion gives lead sulfide, black in color. Sulfide ion plus sodium nitroprusside gives a violet complex. These dramatic color changes make sulfur detection one of the most visual experiments in organic analysis. Halogens like chlorine, bromine, and iodine require extra care. The sodium fusion extract is first acidified with nitric acid. This step destroys interfering ions like cyanide or sulfide, which might otherwise give false results. When silver nitrate is added, halide ions form colored precipitates. Chloride forms a white precipitate of silver chloride, which dissolves easily in ammonium hydroxide. Bromide forms a pale yellow silver bromide precipitate, sparingly soluble in ammonium hydroxide. Iodide forms a yellow silver iodide precipitate, which is insoluble. The general equation is simple. Halide ion plus silver ion gives silver halide precipitate. The colors and solubility differences serve as the fingerprints of each halogen. So, in practice, you don't just look at the color, you also test solubility to be sure. Finally, let's check for phosphorus, which is less common but very important in biomolecules like DNA and ATP. The compound is oxidized with sodium peroxide, converting phosphorus into phosphate ions. When treated with ammonium molybdate solution in nitric acid, a canary yellow precipitate of ammonium phosphomolybdate appears. Another confirmatory method involves precipitating phosphate as magnesium ammonium phosphate, which on ignition yields magnesium pyrophosphate. Whether by a striking yellow color or crystalline precipitate, phosphorus makes itself known. Its detection may be less frequent in simple organics, but in the context of biology and life chemistry, it carries enormous importance. And that brings us to the close of our exploration of qualitative analysis, a set of classical tests that transform invisible atoms into visible, colorful evidence.